Hydrodynamic quantum analogs are fascinating systems where fluid dynamics mimic quantum behaviors. Essentially, in these systems, droplets of fluid, such as oil, bounce on the surface of a vibrating liquid bath. These bouncing droplets create waves on the liquid surface, and the interaction between the droplet and its self-generated waves leads to behaviors that are strikingly similar to those found in quantum mechanics. For example, the droplets can exhibit wave-particle duality, where they behave like both particles and waves, and can even show phenomena like quantized orbits and tunneling. These analogs provide a tangible way to study and visualize quantum effects, making them a powerful tool for understanding the principles of quantum mechanics in a more intuitive and accessible manner. Hydrodynamic quantum analogs, as explored by researchers like John Bush and Yves Couder, offer fascinating insights into quantum-like behaviors in classical systems. In these experiments, droplets of oil bounce on a vibrating liquid surface, generating wave patterns that influence their motion. Yves Couder's pioneering work demonstrated wave-particle duality, where the droplet acts as a particle, while its associated wave field guides its trajectory, similar to the behavior of quantum particles. Further studies by John Bush expanded on these findings, showcasing a variety of quantum-like phenomena. For instance, droplets exhibit quantized orbits around a central point, reminiscent of electrons in atomic orbitals. They also demonstrate tunneling, where droplets can pass through barriers that would be insurmountable without the influence of their wave fields. Another intriguing example is the double-slit experiment analog, where droplets passing through two slits create interference patterns similar to those seen with light or electrons in quantum mechanics. These hydrodynamic systems have even illustrated phenomena such as orbital quantization and spin-like properties, where the droplets adopt discrete energy levels and angular momentum states. By studying these macroscopic systems, researchers like Bush and Couder provide a more intuitive understanding of complex quantum behaviors, bridging the gap between classical and quantum physics, and offering valuable insights into the fundamental nature of particles and waves. One of the most perplexing aspects of quantum mechanics is wave-particle duality. This principle states that quantum entities like electrons and photons can exhibit both wave-like and particle-like behavior. Imagine a beam of light passing through two slits. Instead of creating two distinct bands, as particles would, the light produces an interference pattern, a characteristic of waves. Yet, when we try to detect individual photons, they appear as localized points, like particles. In the macroscopic world, waves are disturbances that propagate through a medium, like ripples on a pond. Particles, on the other hand, are discrete entities with a defined position and momentum. Quantum mechanics blurs this clear distinction, suggesting that these entities exist in a superposition of states, embodying both wave and particle aspects simultaneously. Hydrodynamic quantum analogs provide a unique opportunity to visualize and investigate this duality in a tangible classical system. Yves Couder, a French physicist, was a visionary in the field of hydrodynamic quantum analogs. In the early 2000s, Couder, along with his colleague Emmanuel Fort, conducted groundbreaking experiments. Their setup was deceptively simple: a vibrating bath of silicon oil and a small droplet of the same oil bouncing on its surface. The droplet, instead of merging with the bath, remained afloat, bouncing indefinitely. When they increased the vibration frequency, the droplet started to move across the surface, propelled by its own waves. This self-propulsion was the first hint that something extraordinary was happening. Couder had stumbled upon a system where a macroscopic object, the droplet, was intrinsically coupled to its own wave field, mimicking the wave-particle duality of the quantum world. John Bush, a mathematician at MIT, significantly advanced the field of hydrodynamic quantum analogs. Bush brought his expertise in fluid dynamics and chaos theory to bear on Couder's experimental observations. Bush and his team meticulously recreated and expanded upon Couder's experiments, revealing a wealth of new phenomena. One of Bush's key contributions was the development of a theoretical framework to explain the complex interactions between the droplet and its wave field. This framework, rooted in the principles of pilot wave theory, provided a mathematical language to describe the droplet's motion and its wave-like behavior. Bush's work has been instrumental in establishing hydrodynamic quantum analogs as a legitimate and fruitful area of research. The walking droplet, a quantum ballet, Imagine a droplet of oil bouncing rhythmically on a vibrating bath. As the droplet bounces, it generates waves that spread across the surface. These waves interfere with each other, creating a complex and ever-changing landscape beneath the droplet. In this experiment, the droplet, propelled by its own wave field, embarks on a seemingly random walk across the surface. The droplet's motion is guided by the subtle interplay between its motion and the waves it generates. The droplet becomes enslaved by its own wave field, a phenomenon reminiscent of the pilot wave theory interpretation of quantum mechanics. This dance between the droplet and its waves gives rise to a remarkable phenomenon: quantized orbits. When confined to a circular corral, the droplet's motion becomes constrained, and it settles into stable orbits. The walking droplet experiment provides a striking visual analogy to the behavior of electrons in atoms. The similarities between hydrodynamic quantum analogs and actual quantum systems extend to quantitative predictions. The mathematical framework developed by Bush and his collaborators has successfully modeled several key quantum phenomena. One compelling example is the prediction of quantized energy levels. In quantum mechanics, particles bound to a potential well, like electrons in an atom, can only occupy specific energy levels. Remarkably, hydrodynamic quantum analogs exhibit a similar quantization. The stable orbits of the walking droplet correspond to specific energy states of the system. These energy levels, just like in quantum mechanics, are discrete. Another striking parallel lies in the phenomenon of tunneling. In quantum mechanics, particles can pass through potential barriers, even if they lack sufficient energy to overcome them classically. Astonishingly, hydrodynamic quantum analogs also exhibit a form of tunneling. When a walking droplet encounters a submerged barrier, it can, under certain conditions, pass through it. These quantitative agreements highlight the profound connection between these seemingly disparate realms. The unseen hand pilot wave theory. Imagine a surfer riding a wave. The surfer doesn't create the wave, it exists independently. Yet, the surfer's motion is inextricably linked to the wave's shape and dynamics. This symbiotic relationship is analogous to the central idea behind pilot wave theory. Pilot wave theory, also known as de Broglie-Bohm theory, offers an alternative interpretation of quantum mechanics. Unlike the standard Copenhagen interpretation, pilot wave theory proposes the existence of a guiding wave. In this framework, quantum particles possess both a definite position and momentum at all times. Hydrodynamic quantum analogs provide a tangible realization of pilot wave theory. The droplet, representing a quantum particle, is guided by its own wave field, the pilot wave, which dictates its motion and behavior. A new perspective on quantum reality. The study of hydrodynamic quantum analogs has profound implications for our understanding of quantum mechanics and the nature of reality itself. It challenges the traditional view of quantum mechanics as a theory confined to the microscopic world. These analogs provide a fresh perspective on the interpretation of quantum mechanics. The success of hydrodynamic quantum analogs in replicating key quantum phenomena raises intriguing questions about the universality of quantum principles. They blur the lines between classical and quantum mechanics, suggesting a smooth continuum. The insights gained from studying these analogs have the potential to reshape our understanding of the quantum world and its relationship to our classical experience. Charting the uncharted waters. The field of hydrodynamic quantum analogs is still in its infancy, with vast uncharted territories awaiting exploration. One promising avenue of research involves exploring more complex analogs, such as systems with multiple droplets or droplets interacting with different types of obstacles and potentials. Another exciting direction is the development of novel experimental techniques to manipulate and control these systems with even greater precision. This could involve using lasers to trap and guide droplets, creating artificial potentials to study their behavior, or developing new imaging techniques to visualize their wave fields in greater detail. Refining the mathematical models and incorporating elements from both fluid dynamics and quantum mechanics could lead to a deeper understanding of the underlying principles. The insights gained from studying these analogs could have implications for other areas of physics, such as condensed matter physics, optics, and even cosmology. The principles governing the behavior of fluids and waves are ubiquitous in nature, and the lessons learned from these analogs might find applications in diverse fields. The future of quantum analogies. The future of hydrodynamic quantum analogs is bright. promising a deeper understanding of the quantum world and potentially leading to new technologies. Imagine harnessing the principles of these analogs to manipulate droplets for applications in microfluidics. These analogs could inspire novel approaches to quantum computing, leveraging the wave-like nature of droplets to perform computations. The insights gained from these analogs might even find applications in the development of new materials. By understanding how waves influence the self-assembly of particles, we might be able to design materials with novel properties. The exploration of hydrodynamic quantum analogs is about pushing the boundaries of human knowledge and exploring the uncharted territories of the universe. An invitation to explore. The journey into the world of hydrodynamic quantum analogs is an invitation to explore. It's a call to embrace curiosity, to question our assumptions, and to marvel at the interconnectedness of the universe. So the next time you see raindrops dancing on a puddle or ripples spreading across a lake, take a moment to appreciate the hidden depths of these seemingly simple phenomena. The universe is full of surprises, and sometimes the most profound discoveries are hidden in plain sight, waiting for a curious mind to unlock their secrets.